It's my pleasure to be here. It's my first time in Rio. It's very nice, so thank you for inviting me, and it's especially my pleasure to be here for Carsten's 60th birthday conference. I'm going to talk about critical lockers for complex Henon maps, and let me remind you what complex Henon maps are. Complex Henon map is a biholomorphism of C2 that's given by the formula P of x minus AYX. And it's a biholomorphism. There is an inverse. And it is, in fact, a typical biholomorphism of C2 in the sense that if you take a biholomorphism of C2 with positive entropy, then by Friedland-Milner, it's conjugate to composition of Henon maps. And for one-dimensional maps, the dynamics of the map is to a large extent determined by the critical points. And since Henon map is a biholomorphism, it doesn't have any critical points. So it's tempting to define some analog of the critical points, and critical loci are a natural analog of the critical points. They were defined by Bedford, Smiley, and Hubbard, and they are defined as tangencies between certain dynamical foliations and laminations. So we are going to use, in one dimension, there is a relation between the critical point of the polynomial and the critical point of the green function. So this is the relation we are going to use, or Bedford and Smiley used. So let me remind you the dynamical filtration for the Henon maps. So if you take a Henon map, they exist R such that outside of the polydisk of radius R, when absolute value of x is greater than the absolute value of y, we call this set V plus. When absolute value of y is greater than the absolute value of x, we call this set V minus. All points from V plus go to infinity under the positive Henon map. And for V minus, all points go to infinity under the inverse. And in fact, V plus is a fundamental domain for the escape, for the positive escape lockers. We can, if we define U plus to be the positive escape lockers, then U plus is the union of inverse images of V plus. And the same as in one-dimensional dynamics, we denote the points that have bounded orbit under the forward Henon map by K plus and its boundary by J plus. Our map is invertible, so we have the same objects for the inverse. So we have U minus, which is escape locus for H inverse, and U minus is the union of forward images of V minus, and we define K plus and J minus, and J is the intersection of J plus and J minus. And the same as for one-dimensional dynamics, there is a measure of maximal entropy, and support of this measure is in G. Now I go to the definition of the dynamical foliations and laminations, and let me first start with the, I want to define critical points in J minus. And if I take a point mu almost every point in G, then its unstable set belongs to J minus, and it's a complex one-dimensional manifold. So I can restrict my function G plus to this complex one-dimensional manifold. And if I look at the function G plus in all of C2, there are no critical points. But if I restrict to the one-dimensional manifolds, there can be critical points. And when I take the union of all these critical points of G+, this is CU, unstable critical locus. So this is unstable critical locus defined by Bedford and Smiley. And I want to give another description of this unstable critical locus using a foliation of U+. And I'm going to define this foliation in details later on, but for now I just want to say that there is a foliation of U+ by superstable manifolds. One-dimensional complex superstable manifolds. If 2 points belong to the same leaf, then they converge superexponentially. If they don't belong to the same leaf, then they do not converge. I have not defined G+. I will. I will remind. So at the moment, there is a green function that measures the superexponential rate of escape to infinity. And the formula is very similar to the formula in one dimension. So this unstable critical locus is the set of heteroclinic tangencies between unstable foliation and superstable foliation. And the same way Bedford and Smiley defined the stable critical locus, that is subset of J+. And they also defined the critical locus in the intersection of escape loci U+ and U- as the set of tangencies between superstable and superunstable foliations. And this is the critical locus that I'm going to be talking about. And Bedford and Smiley showed that stable critical locus and unstable critical locus can be empty, but the critical locus in the escape set is always non-empty. Just a couple more words about the stable and unstable critical locus. They define measures, stable and unstable measures on these critical loci, and they wrote formulas for the Lyapunov exponent similar to Prozhitsky-Manin formula in one dimension in terms of these critical measures. So let me now discuss the superstable and superunstable foliations in detail. If we go back to the If we go back to the dynamical filtration, there is on V+ and on V-, there are virtual coordinates that semi-conjugate dynamics. Let's say on V+, it's semi-conjugate, its dynamics to Z goes to Z squared. And this is virtual coordinates in this case is a function from C2 to C. So there are level sets. And these level sets are, at infinity, the virtual coordinate behaves like X. So the level sets, you should think about them as being vertical at infinity. And similarly, for the second virtual coordinate, the level sets are horizontal. So let me go. So these stable and unstable foliations in V+ are level sets of V- and V+. And you can propagate it by dynamics to all of U+ and U-. And these leaves of foliations, Hubbard and Dobbs first showed that the leaves of the foliation are copies of C. And critical locus is tangencies between these two foliations, so it's a proper analytic subset of U+ and U-. Now I finally defined the green functions. G plus and G minus. So they measure exponential escape rate to infinity and the forward and backward iterates of the map. And the same as in one-dimensional dynamics, G plus is log of the Bircher coordinate, and G minus is log up to a constant of phi minus. And we can write the critical locus in terms of G plus and G minus. This is the zeros of one form dG plus. So if G plus is pluri-subharmonic, if you take dG plus, you get a holomorphic function. So a holomorphic one form, one holomorphic one form weighted out the holomorphic one form. The first description of the critical locus was done by Misha Lubitsch and John Robertson, and it was done for the small perturbations. So if you take Henon map h of x, y equals to p of x minus a, y, x, and a is the Jacobian, and you take a to be small. Like if you take a to be equal to 0, then you no longer have biholomorphism of C2. It becomes a one-dimensional map acting on the parabola. Right? You get P of x, x. So this is a one-dimensional map. X goes to P of x acting on the parabola x equals P of y. And if you take a small, you can think about a Henon map as a perturbation of a one-dimensional map. And some of the properties of this one-dimensional map are going to be preserved. So Lubitsch and Robertson looked at the small perturbations of hyperbolic polynomials for which all critical points are distinct and the Julia set is connected. And I won't present the full result. I'll look at the quadratic polynomial x squared plus c. And connected Julia inside. C is inside, not outside. I'm going to look at the outside later on, but at the moment, C is inside the Mandelbrot set. So connected Julia set. Then they fully describe the critical locus for such Henon maps, and the critical locus consists of infinitely many components, and there is a primary component. Primary component C1 that is asymptotic to the x-axis. And it is asymptotic to the x-axis because x equals to 0 is a critical point. So asymptotic to y equals to the critical point. And this component is a punctured disk with a punch at infinity. And on the boundary, it has the stable critical locus. And the stable critical, and I'm going to show the, let me show the picture. This is how the critical C1, this primary component looks like. So it's a punctured disk, puncture is at infinity, and then it converges, it comes to J plus, and it intersects J plus at the stable critical locus, and it is a copy of the Julia set of the polynomial. Okay. And all other components are iterates of this one. And Raluca and Nazi show that the same model holds for quadratic Henon maps with the semi-parabolic periodic point, such that are small perturbations of quadratic polynomials with the parabolic fixed point. Okay. Okay, so one more time, the picture for the Lubitsch-Robertson case. I want to say a few words about the applications. Hubbard and Obersworth described these escape lockers U plus as the quotient of the C times C without the disk D, quotient of this set of this manifold by discrete group of automorphisms. And Reluca used this critical locus to extend this description to J plus. And in the cases when there is a description of the critical, so she used Lubitsch-Robertson description, and she gave a description for the parabolic ones, and she used it in both cases. Okay. So now let me go to the main topic for my today's talk. So I'm going to look at the Henon maps in the HIV region. So I'm going to describe the critical locus for the Henon maps that are not small perturbations. I'm going to look at the quadratic Henon maps. So I'll write down one more time the formula for the quadratic Henon maps. And we say that a Henon map is a shift map if dynamics on K is conjugate to a two-shift on bi-infinite duadic sequences. And we say that we have an HIV region if we have the following inequality. Absolute value of C is greater than beta times 1 plus absolute value of A squared, 1 plus absolute value of A, and the whole thing squared. Should I do what? It's right. It's I should. So yeah, my map on the board is pretty boring. No, easy to study, but we want something more interesting. So it should be x squared plus c minus a y x, right? Like x doesn't go to x. X goes to x squared plus c minus a y. Y goes to x. So its second coordinate is x. So Hubbard, Oberstworth, and show that the maps in the HIV written for certain beta are complex horseshoes, and so they belong to the shift lockers. And I believe Milner showed that beta can be taken to be equal to 2. And let me go to the picture in which I depict HIV beta region. And in our theorem and the description of the critical lockers, for technical reasons, we are going to take beta to be 18.75. So we believe the theorem should be true for beta equal to 2, but for the computational reasons, 18.75 sounds like the right number. Okay. So now I want to give a construction of the main component of the critical locus, and it's a main component because it's not actually a component. The critical locus in this case will be connected. But this is the main building block. So I'm going to take x squared plus c, where c now is actually outside of the Mandelbrot set. So what you see is Julia set that is a Cantor set. And I take an equipotential, one equipotential of P, and I take disk bounded by this equipotential, and I take two of its preimages, and I denote them D0 and D1. And this defines for me coding on the Julia set by the infinite sequences of zeros and ones. It also defines for me the coding on the preimagers of the critical point by finite sequences of zeros and ones. So and I remove the disks around these preimages of the critical point. So I remove the disk W. I remove the disk W empty set around the critical point 0, and the rest of them are parameterized by sequences of zeros and ones. So I have a disk with the Cantor set removed and with a countable collection of disks removed. And I take this disk, I take its copy. And for the top part, I say the disks are W. For the low part, the disks are U. And I denote the upper part by S plus, the lower part by S minus, and I also remove one extra point. And I call this set truncated sphere. Okay. And this is the main theorem for all the C and D in the HAV beta region. The critical locus is smooth and irreducible complex subvariety of U plus intersected with the U minus of pure dimension 1. And it has the following topological model. We take countably many spheres, and we connect the spheres by handles. And if we take W that is on top and U with the same parameterization at the bottom, and we take W on the sphere Sk, we draw a handle to U alpha n of this sphere Skn plus 1, and we denote this handle by gamma k alpha n. So there are 2 to the power k minus 1 handles between Sk and Sk minus 1. So let me show some pictures. Okay. So this is one handle between S minus and between the two consecutive spheres. So if we have two spheres, two consecutive spheres, we have one handle. Now I take sphere S minus and S1. There are two handles. The handles, so in the previous picture, we have handles going from the disk around the critical point to the disk around the critical point. In the next picture, we have handles going from the preimages of the critical point. And in general, this is what we get. So we have like 1 for the next sphere, 2 for the sphere after that, and 2 to the power k minus 1 for the spheres that are at distance k.
Meaning they all connect back to S0?
I'm only drawing the handles from S0. But for the next one, I'm not drawing, I'm only drawing the handles for S0, but there are handles that form from all of them. And the map acts as a shift. So it takes S0 to S1, the handle to the handle.
Go back to the statement of the theorem.
Yeah, I'm going to go back. So these are pictures to keep in mind, to remember. And now I'll go back to the, I try to go back to the theorem. So we always connect we have holes, we always connect the holes of the same level. and the level of the holes tells us to which sphere we should connect it.
So this is an infinite genus surface?
It's infinite genus surface. Yeah, and there are these points, there are also countersets removed, and these countersets are stable and unstable critical lockers. The one on top stable, the one at the bottom unstable. So they don't belong to... Yeah, we remove these countersets from they don't belong to the Riemann surfaces. They don't belong to U plus and U minus, but they are stable and unstable critical sets.
Wait, so I mean, this description here is after you've removed those countersets?
When I define truncated spheres, I removed the countersets.
Is that when the handles came in?
So I defined truncated spheres, there were no handles. So I added the handles in the statement of the theorem. And the last theorem tells us that CS and CU are accessible boundary. The critical locker, the accessible boundary is actually the CS-CU and certainly the critical locus itself. And if we look at the boundary, not just the accessible boundary in C, then it's all of J plus and J minus. Yes?
Any information about the braiding of all these handles between one and the next?
I did not, we did not think about the braiding. That's I think we should be able to, like we have a really good idea how they lie in C2, so we should be able to figure out if there is any braiding, but we did not think about it, so that's something to think about. Yeah.
I was going to ask about the topology of U plus intersect U minus itself, the open set around it. Is that?
Is it? No.
Do you know anything about that? Does it contract onto this?
That's a good question, and that's I thought about it. I cannot pinpoint it. One thing one can write the Meyer-Vietoris sequence that's going to tell us about homologies of U plus intersected U minus. So that's one thing, but the topology, whether it's I don't think it contracts the critical locus. So I don't know. Other questions? Oops. No, don't die. Okay, so pictures, that will be. So I want to explain where these handles lie in C2, like how to see these handles in C2. And one thing is, I want to say where we don't have critical lockers. So there is then picture of the dynamical filtration, and SH delta and SV delta, these long strips of radius delta and delta, it's something like 1 plus absolute value of 8 over 2. If we remove these strips and remove all of the pre-imagers and imagers, then outside we have, in U plus and U minus, we have cones. So it means that we have vertical cones in U plus where we remove the pre-images of SV, and we have horizontal cones in U minus where we remove the images of the horizontal one. So it means that there are no critical locus there. So the critical locus is in the strips or in their preimages or images. And in Lubitsch-Robertson case, it goes along the strip, along the x-axis, and it ends in J+. Here, something more interesting happens. So, like most of our work, like half of our work was that we couldn't really work with the like straight disks and straight strips. We had to make their boundaries to be foliated by the leaves of phi plus and phi minus. So we had to make them dynamical. And that's where this 18.75 comes from. So I think it's a good idea to imagine them straight, but just keep in mind that we are not really working with this straight V. We are working with the dynamical one. So this is a picture where I want to show the handles, where the handles come from. So we have this strip, BH, so this lone strip going to, as a sage strip going to infinity. And the same as in Lubitsch-Robertson case, like there, we have a component asymptotic to the x-axis. And then it enters the dynamical polydisk V tilde, and this is the intersection with the horizontal tube. So we have intersection, this is the intersection with the vertical tube. This is the intersection of horizontal tube with the vertical tube. And we can show that on the boundaries, we have one horizontal disk, one vertical disk. And like if you do some topology, you know that it means that you either have intersection of two disks or you have a handle. And this is like the second half of the job is to show that it's actually a handle. So this is a place where the horizontal component meets the vertical component. And when they meet, they create a handle. This is a handle of level 1, the handle between the two consecutive spheres. So if you take the x equals 0, it goes to y equals 0. So it means that this component under H is mapped to this component.
Can you explain what they are? The middle square is like a polydisk.
This square is a polydisk.
And the tube?
The tube is a tube where we don't have the cones. So
what is the set, like a disk times, is it also like a polydisk?
So the tube is, it's not straight, but you can imagine it, absolute. So this tube is absolute value of y less than delta. And this tube, absolute value of x less than delta. And so these are these are just straight strips. Like we can imagine them as straight strips. And then, so the first handle we can see as intersection of the straight strips, where here we have one component of the critical locus. Here we have second component of the critical locus. Then we have imagers of these strips. And here we've drawn Raluca and Remus have drawn images of the 2 levels. This is level 1. These are, I'm sorry, it's not an image, it's a pre-image. Right? This is image, and this is pre-image. Pre-image of level 1, and these are pre-images of level 2. So these are 2 handles of level 1, and these are 4 handles of level 2. And this arrow, it tells you where does all these handles go under the image of the Henon map. They go to this hole.
Sorry, those are the handles, but where are the spheres?
The sphere is like, if you go to infinity, this is the sphere. The sphere lies, we have here 2 spheres. One lies along the x-axis. The second one is along the y-axis.
So they are like the core of the tube?
They are disks inside of the tube. So if we cut like here and here, then you see a disk with a hole. But if you continue, then you start to get handles. Make sense? So yeah, 2 spheres, one SH is 1 sphere, SV is the second sphere. So SH is what in Lubitsch-Robertson case was S1.
Sphere is like a horizontal line. The horizontal.
Yes.
What's the second?
The second one is the vertical.
How about the third one?
This third one is like here. And there are 2. Right? And this is -2. And like that, then there are 4. And 4 here. Okay. So let me go to the next slide. So I first gave this description for
Two spheres which are connected to your 4 slices of the same sphere. In the previous picture.
Let me go back.
So when you say there are two spheres, the sphere cuts this picture in 2 connected components. So you said there's a sphere.
I said 2 spheres. You're right. The sphere cuts it into, like we see it twice. Yes, Andres, you're right. It's not 2 spheres. It's a sphere that we see twice on this picture. Right? So horizontal and vertical we see once. But once we start to move forward, we see this sphere twice on the picture. Yeah, the same sphere we see twice.
Is it correct to say that it's like having 2 curves intersecting 1 point, like a nodal point? And if you perturb, you get the...
Yes, and this is what I did when I described the critical locus for small perturbations. So if I first described this model for small perturbations of the, when I perturb the polynomial with disconnected Julia set, one sees outside of the Mandelbrot set. And there you can look at the limit when a goes to 0. And you can, you don't have a map, but you have a limit in critical locus. And this limiting critical locus, it does have this intersection. And you perturb it, and you get a handle. And together with Michalevich, we show that for small perturbations, all critical loci are quasi-conformally equivalent. Okay. So in one dimension, we have for quadratic polynomials, we have a dichotomy that if C is outside of the Mandelbrot set, then Julia set is a Cantor set. If it's inside, then it's connected. So we conjecture that critical locus for quadratic partially hyperbolic Henon maps is connected if and only if the Julia set is disconnected. If it's hard to say if it's true to conjecture whether it's true if we remove the partial hyperbolicity assumption. Maybe it's still true. Oops, too fast. So we also looked at the monodromy of the critical locus. So John Hubbard conjectured that there is a rich monodromy group in the shift lockers. Here we can see only two loops. We can see the loop going around the Mandelbrot set, and we can see the loop going around A equals 0. In general, if we don't have a model, we hope that the model of the critical locus is the same in all of the shift lockers, but we don't know that. But if we have the model, then we can look at the monodromy induced by the loops in the shift lockers. So we looked at the monodromy for these two loops, for these two simple loops, one going around A equals 0 and the other going around the Mandelbrot set. So for A equals 0, very simple, nothing happens. So there isn't, it's just identity. If we look at the loop going around the Mandelbrot set, then there is monodromy. So there is an involution that can be described on the Julia set by sending zeros to ones and ones to zeros. And it extends to all, like we can extend it to this disk, and we can extend it to all the critical lockers. Like these rotations, like on each level, it's a rotation by 180 degrees. So the monodromy along this loop around the Mandelbrot set is an involution. And this is it. Thank you. Obrigada, and happy birthday, Carsten.